Welcome to Study Loop.
This problem consists of two proofs that we need to show. Okay, so this is the first one. We want to show that these two sets are equal to each other. Now, for both of these problems that we're going to do here, let's just make sure we have our nomenclature straight. Our function f is a function from A to B. And I'm going to say that x is an element of set A and y is an element of set B such that my function f of x equals y. So just as we do x's and y's throughout here, that's the nomenclature we're going to be using just so we're consistent. Okay, so back to our proof. If I want to show that these two sets are equal, I can do this in two parts. I can show that the left-hand side, that set, is contained in the right-hand side. And then I can show that the set on the right-hand side is contained in the left-hand side. If I can show both directions, that means each is a subset of the other. The two sets are equal. So let's start by saying x is going to be an element of the first set. Okay, so that means that y is an element of the union of s and t. Okay, well, union means that y is either an element of s or y is an element of t. Well, y is f of x. So f of x is an element of s or f of x is an element of t. Well, for the first case, that means that x is an element of the inverse of s, or x is an element of the inverse of t. Okay, well, an or we can put together as a union, which means that x is an element. I'm sorry, miscopied that. If x is an element of that, then that is the second side. So we started with x being an element of the set on the left, and we ended with x being an element of the set of the right. So going this direction, we have proved it. We have showed that the first set is contained in the second set. Now let's go the other way. Let's start by saying x is an element of the right-hand side. Okay, and we're going to show it's going to kind of be the reverse of what we just did. So union means an or. So x is an element of this set or the other. Okay, well, since f of x equals y, I can say that y is an element of s or y is an element of t. So f of x is an element of s or f of x is an element of t. So because it's an or, I could put that together as a union. It's an element of s union with t. So I can also write this as x is an element of the inverse function of s union t. Now that is the left-hand side. So again, this time around, I started with the right-hand side and showed that x was an element of the left-hand side. Since I did both directions, we have proved the equality. Now let's go to the second thing that we need to prove. Okay, very, very similar, except instead of doing unity this time, or union, we are doing the intersection. But we're going to do it the same general format. I'm going to let x be an element of the first set and show that the first set is contained in the second. And then we'll go in reverse. And I'll let x be an element of the second set and show that it is contained in the first. So we will begin. Let's let x be an element of the left-hand set. Okay, since x is an element of that set, then y is an element of the intersection of s and t. Intersection means both, means and. So y is an element of s and y is an element of t. Okay, well, y equals f of x. So f of x is an element of s and f of x is an element of t. So x is an element of the inverse function over s. X is an element of the inverse function of t. And is the intersection, so I can bring these two together. Okay, so I started by saying x was an element of the left-hand side, and I ended with x being an element of the right-hand side. So that direction has been proved. The first is a subset of the second. Now let's go the other direction. Let's let x be an element of the right-hand side. Okay, and let's make that so we can tell what that is. X is an element. Okay, if x is an element of that side, then y is an element. I'm sorry, I don't want to put x in quite yet. I want to break this into pieces first. So since x is an element of the intersection, that means that x is an element of both pieces. Okay, so if x is an element of the inverse of s, then y is an element of s. Same thing here, y would be an element of set T. Since f of x equals y, I can make this substitution. And then I can say that we can put these together. If f of x is an element of both, f of x is an element of s and t, their intersection. So x is an element of the inverse of the intersection of s and t. So in this case, I started with the right-hand side and I ended with the left-hand side. Since I've shown both directions, this proof has been solved.